This is an introduction to the basic chemistry concepts you're going to need in order to really understand what's happening in an honors biology class. A couple things. First, you have to understand the difference between matter and energy. When we talk about matter, it's anything that has mass and takes up space. So that means it's made of atoms. Atoms are the basic unit of matter. They're also the basic unit of any element. Energy is different. Energy does not contain matter. Okay? So elements are matter that is made of only one specific type of atom. Here's an analogy for that. Let's say I go to the grocery store and I want to buy frozen peas. If I go into the frozen food section, I might find a bag of mixed vegetables that has peas and carrots and, lima beans in it. And every single one of those vegetables kind of represents an atom. Each individual pea or carrot represents a single atom. But I might then find a bag that has just frozen peas in it, and that would represent an element because it's only one specific type of matter, okay? This is the 6 most common elements found in living things. Those are shown on the periodic table of elements. You've probably all seen that before. Each of the letters on this periodic table is one specific type. So C stands for carbon, Cl stands for chlorine, Ca stands for calcium, K stands for potassium. So they're represented by those letters. And the 6 most common elements are carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. Put them all together, it spells schnapps, so that's the easiest way to remember that. Okay? But there are certain properties that they all have that distinguish one from another. So, if we start breaking down atoms, atoms are made of protons, neutrons, and electrons. Protons are positively charged, P for positive, P for proton. Neutrons have no charge, or they're neutral, so N for neutral, N for neutron. And electrons are negative, so they have a negatively charged particle. The protons and neutrons are found inside the nucleus of the atom. Electrons are surrounding the outside of the nucleus. They orbit the outside of the nucleus. So here's an example of a lithium atom. Lithium atom has its neutrons and its protons inside the nucleus of the atom, and then the electrons are orbiting around the outside. Now, when we say orbit, we always think of like a satellite going in a big circle around the Earth, but that's not really the way it works. You want to think of it more like a hard-boiled egg. So here's like the egg yolk, where the neutrons and protons are kind of packed in there, and then those electrons are just kind of zipping around all over the place, and they're moving so fast that it's almost like a cloud that surrounds the nucleus, okay? These two would spend a closer amount of time in here, and this one would spend its time kind of all throughout, but a little bit more in this outer shell. So you end up getting these kind of shells formed by these electron clouds. So when we look at lithium, we notice that in its nucleus there are 3 protons, there are 3 neutrons, and then it has 3 electrons surrounding the outside of it. Well, because of this, we know it has an atomic number of 3, and that's due to the number of protons in the atom. That gives it its atomic number. On the periodic table, the atomic number is located right above the letter, so it's at the top of the box, and this represents the number of protons found in the nucleus of the atom. Each element has its own unique atomic number, okay? So if we look at the different elements here in the periodic table, oxygen has 8 protons. Fluorine has 9 protons. Hydrogen has 1 proton. Okay, you can tell just by looking at the periodic table, finding that atomic number, that's how many protons there are. If you change the number of protons, that makes it a whole different element because now it has a different atomic number. So if I were to somehow take carbon and I were to take away 2 protons from it, it would now become beryllium. Okay, or if I were to take oxygen and take away 2 protons, it would become a carbon atom because it would have a different number of protons. The number of protons determines what the element actually is. Now, if you also look underneath the letter, you see another number. That's the mass number, also called the atomic mass. that represents the actual mass of the atom, because protons plus neutrons together give it the mass. Okay? This is sort of a decimal number. It's not a whole number. When you're given an atomic mass, sometimes it'll just be a whole number. If I ever give it to you, it'll be a whole number. And you can tell by taking the atomic number and subtracting it from the mass number, and that tells you how many neutrons you'd have, because this is protons. This is protons plus neutrons, so you subtract the protons, that gives you neutrons. Now, the number of protons and neutrons are not always the same in every atom. So some elements can have different versions of them that have different numbers of neutrons. So these are called isotopes. Here's a couple of examples. So uranium is found as uranium-238 and also as uranium-235. Hydrogen can be found as H1, H2, or H3. These numbers represent the mass number, okay? And what happens is, as uranium naturally decays, it loses neutrons from its mass. It's still uranium because it hasn't lost any protons, and it loses, in this case, 3 neutrons to now have a mass number of 235, okay? So this is the reason why this mass number is actually a decimal number instead of just a whole number, because what they do is they look at all of the magnesium, for instance, that's found in the universe and all the different various isotopes that are there, and they look at the frequency that each isotope is found, and they average all those together, and they end up getting this decimal number, which is telling you the average mass of magnesium that's found in the universe, okay? We're just going to deal with it in terms of whole numbers. All right, but isotopes can be important for, biology as well. Here's an example. As uranium continues to decay, it actually does start to lose protons. What happens is there's a several stage process it goes through, and eventually it becomes radium, and then radium decays by losing a whole helium atom out of it. So it loses some protons, neutrons, and electrons, and it becomes radon. Okay, and radon is a radioactive gas that you might find in your basement that could actually be harmful to you because it's radioactive. All right, but here's an example of where naturally the number of protons has changed, so it has actually become an entirely different element. Okay, this is part of the process they use in a nuclear power plant to generate the heat that becomes electricity. Other important radioisotopes are carbon-12 and carbon-14. They're both used for radiocarbon dating because we know it takes 10,000 years for an isotope of carbon-14 to decay into carbon-12. So they can take a sample of something like a bone from a fossil or, an old clay pottery piece or something, and they can measure the different frequency of the radioisotopes of carbon and figure out a pretty good age for that piece of fossil or whatever it is. Also, barium is radioactive, so it can be used to kind of tag parts of organs, either by injecting dye into them, or my son had to have this done. He had to drink a barium milkshake so they could look at his GI tract like you see here. And then you look at it through an X-ray, and the radioactivity that's given off from those isotopes changing into different isotopes is able to be seen on an X-ray, and you can look at the different organs. Okay? Radiation in its own form, that's coming from like the decay of uranium, can be used as a cancer treatment when people get radiation therapy to sort of kill the cancer cells. And the last thing that you need to know is if you somehow change the number of electrons in an atom, if one atom takes away electrons from another one or it gives ones to it, it then becomes an ion, which either has a positively or negatively charge to it. So if it takes an electron away and it gets an extra electron, it's going to have a negative charge. If it loses an electron, it's going to have a positive charge. And we'll go over that a little bit more in class. So that's the end of the first video. Make sure you watch the second video to learn about bonding.